let's talk about the energy involved in forming a solution. So we can imagine this happening in 3 steps. Here we have our solute. Let's just say it's a solid. Well, in order for this solute to dissolve, say, in water, we have to separate the particles from each other. They are sticking to each other because of intermolecular forces. So we have to put energy in to pull them apart, to make them ready to be part of a solution. So this process is always going to be endothermic because we have to break those attractions. So delta H for separating the solute molecules is going to be a positive number. Then we also have to separate the solvent molecules. Let's just call these water. So we've got these water molecules, and they're all together as a liquid, right? Why are they sticking together? Because they have intermolecular forces. Well, in order for a solute to get in here, we have to separate the particles. So this is also going to be an endothermic process. So separating the solvent molecules is going to be a positive change in energy going into the system. And then we have the third step where we take the separated solute particles and the separated solvent particles and we mix them together. What's going to happen here is that we're going to form new interactions between particles. And so here, this will be exothermic because as those particles interact, energy is released. So delta H for the mixing is less than 0. Any questions? Mm-hmm. There's not a simple relationship between entropy and enthalpy.
Okay.
No. If you take Chem 1B, you'll learn a lot more about that. But
Okay.
yeah. So the enthalpy of a solution forming is the sum of all of those changes, those 3 steps. And so the overall sign is going to depend on the magnitudes of those. If we have all of the positive ones are big and the negative one is small, then overall the sign is going to be positive. But it could also be negative. And so solution formation can be exothermic or endothermic. Here we've got 2 different examples. We're starting with I'm sorry, I just noticed that there's this weird pink thing in there. I have no idea what that is. Sorry. It must be a squirrel is what it is. Here we have the solvent and solute particles are aggregated. They're stuck together. And so we have to put energy in to separate the solute particles. We have to put more energy in to separate the solvent particles. And then when we allow these to mix, energy is released. So in this case, more energy was released than what we had to put in. And so the net difference, delta H for the solution, is a negative number. It's exothermic. The solution is giving off energy. And so this would feel warm to the touch because energy is coming out of it. Here's an example where we have to put more energy in than what's released. And so here it's a net endothermic process, and this solution is going to feel cold because where's that heat coming from? The heat is coming from the surroundings. So if you're holding the beaker, it's drawing heat out of your fingers, so it feels cold. Well, if we're just talking about aqueous solutions of ionic compounds, which is most of the things, we can take that delta H solvent and the delta H mixing and add those together and call that the heat of hydration. So that's the enthalpy change that happens if or when 1 mole of gaseous solute ions is dissolved in water. That's always going to be negative. Because the ion dipole forces that form are much stronger than the hydrogen bonding that was broken. So delta H for the solvent is taking the water molecules and separating them from each other. So you're breaking hydrogen bonds. Delta H for mixing is when you've got the ions and the water molecules coming together, and they're going to have these ion dipole interactions. Those are much stronger even than hydrogen bonding, and so this is going to be an exothermic process. For ionic compounds, delta H for the solute, remember that's the energy needed to separate the solute particles from each other. That is the same but opposite in sign as the lattice energy we learned about before. So lattice energy is taking blah, 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 blah. Remember that lattice energy was when we had separated ions and they came together. Remember that picture? They came together and they're all attracted to each other. Right? So that was the lattice energy. Delta H for the solute is the opposite of that. We're taking the ions that are all stuck to each other by ionic bonds and we're separating them into individual ions. So that is the same value as the lattice energy, just opposite in sign. So we've got that happening, and then we have the heat of hydration. And depending on which is larger, the solution process can be exothermic, the solution will feel warm, or it can be endothermic and it will feel cold.